I think we can get started. So the next talk, the first talk of the day, is going to be by Mirabel Reid from Georgia Tech, who's going to talk about understanding in LLMs.
Hi, everybody. So I'm going to spend the next about 10 to 15 minutes here talking about the topic of whether large language models can understand algorithms. This is joint work with my advisor, Santosh Vimpala at Georgia Tech in the School of Computer Science. So here's a quick outline of the talk. First, I'm going to motivate the question, why are we interested in algorithm understanding in particular? Second, I'm going to pose the question, can AI understand at all? Can a large language model understand? Third, I'm going to define our hierarchical scale of understanding. And lastly, I'm going to briefly talk about a study we did comparing students and large language model abilities with algorithms. So first off, why study understanding of algorithms? Well, there are two lenses we can approach this question. First is a practical lens. Large language models are currently used in practice to generate code and to assist novice programmers in learning. So that begs the question, to what degree should we rely on them? If they're good at generating code, does that mean they're going to be automatically good at teaching? Identifying understanding and defining it well can allow us to understand who to trust. We can also look at it from a conceptual lens. I want to disambiguate algorithm understanding from language understanding. So we had a bit of discussion yesterday about the concept of grounding, where a large language model can represent the token apple, and it can tell you facts about apples, but it's never experienced the physical object that we have in the real world. But with algorithms, it's a little bit different. It's a formally defined object, a process rather than something that exists in the physical world. And it can be completely represented in computer memory. Now, that doesn't mean that we completely escape the topic of grounding. For example, a student might partially understand a shortest path algorithm by their experience navigating to work. However, the fact that the core object that we're dealing with is formally defined is going to help us. So we know that a large language model can store an algorithm in its memory, but can it understand it? Well, first, let's ask a simpler question. Can my laptop understand an algorithm? So on my laptop here, you'll have to trust me, I have a program called gcd.py. It can take any two integers and compute the greatest common denominator. As long as it fits in its memory, it does this almost instantaneously with 100% accuracy. Think about that, 100% accuracy. We could never expect a human to be able to do that. Not only that, but it can also tell us what it's doing. All I have to do is ask in a language that it understands here, and it'll output exactly the code it used to compute the greatest common denominator. And with a bit of finagling, I can get it to do step-by-step calculations and tell us how it does each step to calculate the greatest common denominator. So most of you would probably agree that my laptop is dumb and it doesn't understand anything. But let's probe this a little bit. So one explanation for this is that understanding is an internal state. It requires language or reasoning or a world model, something that we have and my laptop doesn't. But suppose that the entity we're posing is a black box. We don't want to know anything about its internal state. Can we still determine if it understands? Well, at this point, this is the Chinese room experiment, right? This is an argument that was started by John Searle. And the debates have been going back for decades. And even if I was an expert, I could not summarize it in 10 minutes. So for now, let's just take this as a given. We want a purely functional view of understanding that is quantitative and task-driven. If this is our goal, what choices of tasks should we choose? So let's look at the overall goals of our framework. We want the following properties. It provides a scale by which to evaluate any agent's understanding of an algorithm, be it AI, large language model, or human being. It aligns with the standard usage of the term understanding in fields like philosophy and psychology. And it can evaluate a large language model's progress toward understanding algorithms. For this, we can take some cues from educational psychology. So we'll categorize the topics the tasks that we're looking for into cognitive processes and make a distinction between shallow and deep learning. So first, let's start with some shallow, basic cognitive processes that are associated with understanding algorithms. At the top level, level 1, we have execution. So at the very base level, the agent should be able to execute the algorithm on some simple examples, which means it has some kind of representation of the input, the output space. It knows what it does, and given a simple example, it can tell you what the output is. At the next level, it can do more complex calculations. So for any inputs that would fit in its memory, or where the calculation would fit in its memory, it can produce a step-by-step evaluation that produces the correct output and tells you how it did it. And the third level is precise representation. So the entity, the agent, can tell you exactly how to compute the output for any two inputs. This can be a natural language explanation, or it can be code. So you'll notice that these three things are what I just said that my laptop can do. So we haven't made any progress towards saying that my laptop is dumb. So let's move from this shallow level understanding into something more deep. So at the next step, I'm going to make a differentiation between cognitive processes that use mathematical reasoning versus cognitive processes that use natural language. On this side, we want it to be able to produce examples. So what this means is that the agent can not only work forward to compute the algorithm and go through the steps, but it can also work backwards. If we give it a property that we want, it can come up with an example that satisfies the property of the execution. On the other side, we want it to be able to explain it. Now, an explanation is difficult to formally define, but it is important for understanding, and we want to have it in our categorization. So at this level, it should be able to summarize the algorithm, explain it in different ways, and tell you, like, why is this part here? Why is this part here? So these are clearly a more difficult cognitive task than what we have above us. But we're still within the domain of the algorithm. At the next step, we want to be able to look at extensions. So at level 5, the algorithm can, or the agent can answer counterexamples and deal with counterfactual questions. A counterfactual question is kind of a what-if question, which asks about modifications to the current reality. So in the context of algorithms, we can think of a modification to the algorithm. Suppose we have a slightly different algorithm, which does it a little bit differently. Does it still work? Can we find an example where it doesn't work? And furthermore, can we use our knowledge of other algorithms to extend what we know about this one and answer questions that are outside of the domain? So we have this simple scale. Can we use it to evaluate understanding? So this brings us to a study that we did with students in large language models. So we made a 5-question survey with 2 versions corresponding to either the mathematical reasoning or the natural language reasoning, with 1 question for each level. This survey was given to both student participants with 10 doctoral and 24 undergraduate, all in math or computer science, and 3 versions of GPT, 3.5, 4, and the brand new 4.0. To assess understanding, we chose 2 candidate algorithms. The first is the Euclidean algorithm, which computes the greatest common denominator of 2 integers. This is very simple, and it's often the first introduction of the concept of the algorithm to a student. The second is the Ford-Fulkerson algorithm for maximum flow, which was created in the 50s. If you did an undergraduate degree in computer science, you've probably seen this. If you didn't, you've probably never seen it in your lives. But it's something that is taught in upper-level undergraduate algorithms classes, and students often kind of struggle with it. So let's see how they did. So we graded each of the 5 questions on a scale from 0 to 2, and we rated each of the participants on it and computed the average. For the large language models, they were prompted with chain of thought reasoning to give them the best chance to answer the questions correctly. And it was done over many trials with random variants of the question. So we see here kind of what we expect, where GPT 3.5, the oldest version, did the worst on all of the questions except for coding. So this question asked them to produce code or fill in the blanks for code for the algorithm. And all versions of GPT did very well. So if we compare this to students and take the best performing version, which was GPT-4, we see that GPT-4 did much better than undergraduates on the algorithm and about at the same level as the doctoral students. We can also break this up by algorithm. We can see that the scores on the GCD were much better than the scores on the flow, which makes sense for the students because it's an easier algorithm to learn. And it also makes sense for GPT because there's a lot more information on the Euclidean algorithm available than on the Ford-Fulkerson algorithm. And finally, we can break this up into our two categories of mathematical and natural language reasoning. So we actually see something interesting here. So for each of these trees, the left side is mathematical reasoning and the right side is natural language. And while it does well overall, it does a lot worse on the mathematical reasoning than on the natural language reasoning, which is kind of what you expect, but there is some surprising things that come out of this. In particular, it's not just due to calculation. So we specifically chose questions where students don't really have to run the algorithm in their head in order to answer them. They should be able to answer it based on sort of intuitive understanding of the input space. Despite this, GPT really struggles with it. So I think that this does elucidate something interesting about understanding of algorithms. And we have a similar thing for the Euclidean algorithm where everybody does very well. And finally, I want to advertise that this has just been posted on arXiv, so if you want to see more about the experiments that we did, it's hot off the press. And thank you. I'm happy to take any questions.
The one in the sort of bottom left that undergrads in GPT sort of struggled the most with, I guess on the slide before that, could you give an
this one?
Yeah. Could you give an example of what the questions actually are in that one?
Yeah, sure. So the one that I thought was interesting, it basically asks the student to come up with a graph where the Ford-Fulkerson algorithm needs 6 augmenting paths. So this question seems difficult at first because 6 is kind of a big number. But every single student we asked came up with this simple example, where you have 1 source node and 1 sink node and 6 parallel paths. So you don't need any calculation to answer this. But GPT was never able to come up with a solution, even when prompted with chain of thought reasoning.
Is this like a representation issue? So people think people have to do it visually or
Is this a representation issue? So people will do it visually, but GPT-4, I guess, does it in text?
I think that's possible. So for this particular question, we didn't give them any pictures. But there's nothing really we can do about a student, using paper to sketch it out.
Of course.
So that is like I think a limitation of the type of reasoning that GPT can do.
At the start of your talk, you asked the question, do you need language in order to understand? I just wonder what you think. Do you need language in order to understand?
Personally, I don't think so, because I think that there are things that non-human animals can understand. But I think that there are certain things, certain tasks that you need language to be able to do.
Thank you.
Yeah, this is really interesting. So one important dimension of understanding is being able to connect a domain to other domains. So I was wondering whether you did anything like that here. For example, on the GCD question, one minimal thing would be extending from arithmetic to geometry. So prime numbers and composite numbers. Or could you have a rectangle of this size? And then maybe even ultimately, applying it to other domains too, like say social domains and dividing things into groups. Was there anything here which tested connections outside the mathematical domain?
We tried to do extensions to other things within mathematics, but we didn't try to do any sort of social element or applications.
Okay, cool. By the way, do you have a list of the questions? I'd just be curious to see them.
Yes, they're in the appendix of the paper.
So a model like GPT-4, for example, if trained on like a huge amount of text from like the internet, say, like the average person on the internet might not be like an advanced graduate student in computer science. And so if it's sort of producing an output for that based on its statistical understanding, it might be drawing from like the average person. And so producing responses like this. So do you think if you gave it like some context at the beginning that sort of like made it think that it was an advanced graduate student, that it might actually be able to produce like a distribution on this type of thing, like these types of results that looks more like the sort of like doctoral students that you see?
That would be an interesting thing to try. What we did is we included a system prompt that was just the same across all things. That was like, you're an expert on algorithms. You can answer these questions about the following algorithm. But I think it would be interesting to do a comparison to see if that works.
I actually have the opposite question. Like, how do you know, like, I would assume that this is in the training data for these algorithms, right? These are such basic, textbook material algorithms. They probably trained on it. So I'm wondering, how do you think that affects your results, and like whether maybe it's a good idea to do something where you invent some algorithm, something like that. It kind of relates to Leslie's educability, right? You teach it some algorithm, and then you ask questions about that.
Yeah, that is a great question. So we say nothing about learning here. In fact, these things are absolutely, definitely in the training sets. So what we argue is that it understands it in the state that it is. But it doesn't say anything about whether you can teach it to learn something else.
I just wanted to tell Manuel, there's a paper that just came out last week here from Berkeley about exactly the question of whether you need language to think. I'll send it out. It's an interesting. Yeah. It's from Stephen. He couldn't come because he's on paternity leave, unfortunately, but it's a very cool Nature paper.
I did think about it.
Yeah, the language. Yeah, language for reasoning. Yeah. Yeah. And you should
Great, thanks. Actually, to follow up on Sheely's question, if one of the hallmarks of really truly understanding something at an expert level is that you can on the fly come up with an analogy or a metaphor or something like that, where you can kind of completely change the surface level features of the problem and yet explain it to another entity, another agent, in a way that you think that they're going to understand using language. So I'm wondering if maybe for these algorithms, a lot of analogies and a lot of other explanations exist in the training set, absolutely. But if you were to go towards one where you're coming up with a new algorithm, or you explain the algorithm using analogy and see if it can actually connect back to the thing that's in its training set, whether playing with something that doesn't use the surface level features that would be that would allow the GPT to essentially look it up in a lookup table, but that would test the core level understanding and be like, is there something that this makes you think of? So I was wondering if you thought about analogy and how that might play a role.
Yeah, so we asked it some questions that are like, can you explain it in this particular context or with regards to this particular application?
Sure, but that's not really the same thing as an analogy, right? Yeah.
So I think
Okay.
that would be an interesting future direction.
Thanks.
Okay, let's move to the next talk by Paul Liang from CMU about multisensory AI. And, give you a round of applause.
Hey everyone, is this working? Hey everyone, thanks for coming. So today I'm going to talk about some scientific principles of multisensory AI. And this is a topic that we've been discussing quite a bit in this workshop. How can we ground large language models with all aspects of the multisensory world, combining spoken words and language with visual data, with audio data. And in fact, there's many, many more sensory modalities that we didn't talk about, but yet exist in the world, including things like medical data. Can I use language models to better understand and interpret these medical images? Can I use large language models to understand physical sensors in the world, including IoT sensors and so on? And all this diverse range of modalities in the world, including things like data on your smartphone, data from your physical activities, social networks, activities, and so on. And this is a huge topic nowadays. But despite all the empirical progress in multimodal learning, we have some very basic questions. We've seen a lot of debates over the past workshop on whether LLMs are actually grounded. Language-only models, are they grounded in these sensory modalities in the world? Is language sufficient as a representation? Are there going to be some platonic representations where if you train models on all these modalities, do they end up converging to the same features? And why is it that sometimes when we train these multimodal models on data that we believe should be useful, such as the talks on attaching cameras and audios to children, how come multimodal models don't outperform simple unimodal baselines? And a lot of these debates exist because we don't have principles for multimodal learning. We have lots of empirical progress, but we don't have any scientific principles in this field. So what do I mean by principles? Principles might constitute answers to the following basic questions. Like, for example, what information is in a modality? What type of information and what amount of information? How does this information change in the presence of other modalities? Maybe because there's some correspondence between modalities, or there's some new information that arises when we fuse two modalities together. We don't know what are the right models that are the most suited to learning this type of information from multimodal data. And finally, if I train a multimodal model, we don't have any understanding of whether this model is actually making use of this multimodal information, or is it simply using some surface-level statistics from language-only or vision-only data. So my goal in this talk is to illustrate some of our recent progress towards building a more scientific understanding and building up these principles for multimodal machine learning. Again, this is a long-term research question. I don't claim to have answers to all of these questions, but hopefully what I present today is going to be a good starting point for answering these questions. Now, a lot of these questions arise from the study of multimodal interactions. This principle that when you have different modalities, there is some information contained within those modalities themselves, and also some information that arises when you combine or fuse them together. And there's several classic examples of this. I'm going to use these modalities X1 in red, modalities X2 in blue. And in the most general case, you can think of these modalities as having some overlapping information. For example, parts of the caption describing parts of the image, and at the same time, some unique information in the visual domain and some unique information in the language domain. And I'm going to use this third circle, Y, to represent some task that you're trying to predict. And in general, there's three types of interactions you may care about. The first type of interaction is that of redundancy, where there's common information between both modalities that is relevant to the task. And one example of this is when you're saying something positive, like this movie is great, with a huge smile on your face. Both of those indicate positive receptions to the movie, and together they indicate that you really, really like the movie. Another key interaction is that of uniqueness, when there's unique information present in one modality, but which is not present in the other one. So think of saying something slightly positive, like the movie does a good job developing the characters, but with mostly neutral facial expressions. And out of these, one of the modalities has the unique information that is important for the label. And the third type of interaction that I love the most is synergy, where there's some emerging information when you combine these modalities together, but this information wasn't present in the modalities to begin with. So think of saying something positive, like wow, which seems positive, but with negative, angry, or frustrated expressions on your face. And it's a disagreement between these two modalities that indicates that a person is actually being sarcastic. So you can already start thinking, different types of interactions would definitely lead to different types of performance. Right? Multimodal performance should improve substantially if there is some synergy in your data, but we don't expect multimodal performance to improve when there's only unique information in language, for example, or redundant overlapping information between language and other grounded modalities. And because we're looking at building more principles, I'm going to go one step further in coming up with a precise mathematical definition of each of these interactions. So again, we assume that we start with some joint distribution P. So this joint distribution is going to be over your two modalities, x1, x2, and your label y. And together, these modalities give some total information towards predicting label y. But the goal is to decompose this total information into which part of it is redundant, so shared between two modalities, is unique to the first and unique to the second, and how much of it is synergistic, that arises only when you fuse these two modalities together. And to present this mathematical framework, there's going to be two key ideas. The first key idea is that if you have this joint distribution P over two modalities and a label, you can infer two other distributions. We call these unimodal marginals. So a distribution over only x1 and y, so we marginalize x2 away, and a distribution over x2 and y, so we marginalize x1 away. And the key idea is that if you look at these unimodal marginals, you can separate redundant and unique information versus synergistic information. Specifically, the fact that redundancy is encoded within these two unimodal marginals. For example, x1 is positive, x2 is positive. Just from those two marginals, you get that there is redundant information in your data. For uniqueness as well, x1 was positive, x2 was neutral. Just from those two marginals, you can get that there's unique information in your data. But this doesn't work for synergy, right? If x1 was positive, you're saying something positive in language. You're showing something negative in your expressions. Without knowing the true multimodal label, you cannot distinguish whether it's unique or synergistic. If the true multimodal label is positive, then that's unique information in the first modality. If the true multimodal label is negative, then that's unique information in the second modality. And if the true multimodal label is something completely different, like the person is being sarcastic, only then is that synergistic information. So therefore, that brings up idea two. If you look at these unimodal marginals, you can actually infer how much redundancy and uniqueness there is, but you cannot infer how much synergy there is. Here's an example, right? You took x1 being positive, x2 being positive. You create a joint distribution where x1 and x2 both lead you to predict positive outcome. And because that distribution is the same as the real distribution that you started with, that means there was all redundancy in your data and there was no synergy. Same thing in the second case. If x1 was positive and x2 was neutral, you can create a joint distribution given those marginals, where given x1 and x2, you take the first label that is positive. And again, because that is the same as the original distribution that you started with, that means there was all uniqueness and no synergy in your data. In the third case, you could take x1 being positive, x2 being neutral. You could combine them in all sorts of ways to create a multimodal distribution, which is given the both modalities, either positive or negative. But because this is very different from the true distribution that you started with, which is the person being sarcastic, that means you're losing out on a lot of information when you only combine these unimodal marginals. And that information that you lose is the synergy between both modalities. And to make this more formal, what we essentially did is that we started from a joint distribution P over two modalities and a label. We inferred a unimodal marginal over x1 and y, and a marginal over x2 and y. And we considered all these intermediate distributions Q over x1, x2, and y, where Q is a coupling of these unimodal marginals. And by coupling, I mean that Q of x1 and y is equal to P of x1 and y, and Q of x2 and y is equal to P of x2 and y. Making sure Q stays within these couplings keeps the same amount of redundant and unique information while changing the amount of potentially synergistic information. And that therefore means we can find the minimum distribution in Q with the least amount of information, which keeps R and U the same, but pushes synergy down to 0. We know that the total information, the x1, x2 contributes to y, has redundant, unique, and synergistic components, which means that a formal definition of synergy is the difference between these two terms. How much total information your two modalities contribute to y minus the worst way of combining these modalities, which gets rid of all the synergy between those two modalities. Now, this may seem scary, but in fact, computing this term, computing how much synergy two modalities combine to create new information is fairly simple. It is basically the solution to a max entropy problem. So looking at given x1 and x2, what is the worst distribution that gives you the worst performance on predicting y, subject to these constraints, making sure that this distribution follows the p of x1 and y marginal and p of x2 and y marginal. And therefore, if x1 and x2 are small and discrete, this is basically a convex optimization problem with linear constraints. You can solve this in a matter of milliseconds. If x1 and x2 are high-dimensional and continuous, it becomes more challenging, but in our paper we propose an approximate estimator that learns the features from continuous data and solve this optimization problem to derive how much synergy there is when you combine two modalities. And there's several key ideas here. The first key idea is that computing synergy requires knowing the full distribution, how much x1, x2, and y paired data you have. But computing redundancy and uniqueness only requires knowing the marginals. So just from x1 and y, and x2 and y, so perhaps language model that you've trained and vision model that you've trained, you can run these equations and compute how much overlap in information or uniqueness in information there is between these two unimodal marginals. Another key idea is that, as I mentioned, because this is just a convex programming problem, approximately quantifying these measures is much, much faster than looking at your data, then choosing what model to run, then training these models, and so on. So in fact, understanding these interactions can be a good prerequisite to deciding what models to use and how to train them, as we'll show in the next couple of slides. And I also want to emphasize that information theory is just one formal construct. We can relax this assumption. We might not want to use information theory and relax everything here into some form of other dependence. For example, whether you can train a classifier from x1 and x2 to y while subtracting off what is the worst possible coupling of unimodal classifiers, how much x1 tells you about y and how much x2 tells you about y. So in fact, this framework can also be extended to use correlation between your modalities in the label and other probing tasks, how much features learned from a single modality is able to predict the label. And finally, in subsequent work, we also showed that instead of computing this equation for synergy, one approximate way to define synergy is how much the two modalities disagree on predicting a label. The more disagreement there is, for example, language tells me I'm positive, I'm saying something positive, and vision tells me I'm negative, I'm showing angry expressions. The more disagreement there is between your modalities, that gives you a lower bound on how much synergy that can arise when you fuse these modalities together. Well, this is another way of approximating how much synergy there is. And also show some examples, right? So if you run these estimators on real-world data, you can look at expressions of human sentiment. You're saying something, you're showing expressions, you're showing audio and speech patterns, and you're trying to predict whether a person was happy or sad about a topic. And in these settings, there's a lot of redundancy and also unique information in language. And that makes sense because we typically say positive things and we say negative things. And we back that up with positive expressions and negative expressions. So in fact, a lot of this matches human judgment of interactions. Another example we considered was people being sarcastic. We use this as a motivation, but in fact, we actually found that sometimes people were sarcastic using language only, but in many other settings, there was lots of synergy between modalities. So people were saying positive things while showing negative expressions, and therefore that necessitated fusion of these two modalities to predict whether a person was being sarcastic. Let's go over a few slides, and I'm also going to show some of our recent applications of this work. So in fact, we looked at different types of interactions, where the data is redundant, unique, and synergy. And we actually find that if you train just one large model, one BLIP2 pre-trained model on this data, it works really, really well on settings that are redundant. A lot of these modern vision language models are trained to exploit the fact that there is common information in language and images. So they perform really well in the presence of redundancy. But these models start performing really, really poorly when there is some synergy in your data. Right, in the sarcasm case, where there isn't sarcasm in language only and vision, but only when you combine them together. And a natural application of this idea of understanding these interactions is to train what we call this mixture of experts, where you can start taking your data, you can perform this quantification to divide your training data set into parts that are redundant, parts that are unique, and parts that are synergistic, and train individual experts suitable for each type of interaction. And when you're given a new test data point, you can try to use inference by essentially categorizing which expert model I should use, given on what type of interaction is present in the data. And this mixture of experts idea is something that's really broadly applicable. You can apply them to fusion models. You can apply them to multimodal language models like VLMs. You can also apply them to settings where you first caption the image into text, and you have a language, and you're trying to fuse them both using a language-only model. And some cool results we've been able to get recently is that it's really improves performance, especially for settings where there's lots of synergy. Right? These large language models, large vision language models may struggle when there's synergy in the data, but when you start training these expert models that are tailored towards learning the synergistic information, they perform much better, more than 15% improvement on these settings. And so they work in cases of sarcasm. They work in case of figurative language. Like, you have an image here and your caption is, the car is as fast as a cheetah, when there actually isn't a cheetah in the image. It works in case of humor, right? You have these images with lots of people sitting around the room with really large cups of milk. And the caption is, can you please pass the cow? Instead of, can you please pass the milk? So all these settings where there is some more unique and synergistic information for figurative language and humor. So to end the talk, I want to summarize what we just looked at today. We looked at trying to build up a principle for multisensory AI. And this principle constitutes 3 questions. Can we understand what interactions are in my data? Is my data primarily redundant with overlapping information between your modalities? Where there's unique information in one and not in the other? Or how much can I quantify the synergy of information? How much new information arises when I fuse these modalities? We looked at how we can quantify what interactions these models are learning, and finally choosing the right models that are suitable for my data, including using mixtures of experts models that learns a redundancy expert, a uniqueness expert, and a synergistic expert, which is well applicable to many settings. And finally, because Sherry wanted us to end with some open questions, some open questions I personally believe that are going to be very important within a science, engineering, and multimodal models. Firstly, understanding cross-modal learning. We've been looking at multimodal fusion, whether A plus B, 2 modalities give you better ability to predict some label Y. But another debate is whether learning A plus B, 2 modalities jointly can improve the learning of a single modality. For example, when you train language models, should you train language models in the presence of images? And does that improve language learning? How can we come up with a formal definition of that? High modality and partially observed learning. We're going to go beyond fully observed paired data like image and text to settings where you have image and text, but image and audio, image and other sensors. How do you learn from these settings? And also various applications of multisensory integration inspired by neuroscience. The fact that there's multiple multisensory integration areas in the brain, which gives credence to the idea that there should be AI models that use mixture of experts to fuse modalities. That despite that fact, there's also multisensory neurons within unimodal cortexes. That also means that there might be some amount of early fusion that is done, not just vision processing until fusion, but even the initial stages of visual processing have some multimodal information with other modalities. And finally, cross-modal plasticity. Today's AI models don't do this, but how can we build multimodal models that when one modality is removed, automatically shifts towards learning information from other modalities? All right, thanks everyone. Happy to take any questions.
We have time for one quick question.
Yeah, thanks so much. I was really happy to see this list of neuroscience-related or inspired foci at the end. I had 2 others that I kept coming back to throughout your talk, and I was wondering if you could speak a little to them. The first is the principle of inverse effectiveness, that you see more efficacy or more benefit from having multimodal input in learning or even in just kind of sensory processing when both signals are very small. And so I was wondering how you're seeing any principles of inverse effectiveness in any of the data sets that you're looking at. And the second one was, when we talk about multisensory integration or multimodal integration from a human neuroscience perspective, we also see plasticity of not just the multimodal inputs themselves, but a prior over the tendency to integrate it all, the probability of a common cause. So I was wondering if you are seeing in like training these any plasticity or context dependence in the probability of integrating it all, or how that interacts with the synergy component.
Those are both great questions. I think the first case, let's clarify what you mean by small. You said when that's one.
Yeah, when in multisensory integration in humans, which is where I'm coming from, if you have 2 very small, very noisy signals, like the signal-to-noise ratio and auditory and visual inputs are really bad, then you see a proportionally larger benefit from having that multimodal input than you would if either one of those signals was strong or if both were strong.
I mean, that's a good question. I think that our model accounts for that because if there's lots of unique information, when the two signals are noisy, for example, then there's more chance for the other modality to have unique information, and therefore you need to look at the other modality. So if I can extend some of this framework to settings where you have noise or imperfections, in that case, it still works for understanding what the information arises when you start combining these modalities to uniqueness and synergy. For a second question, so could it be a second question as well?
About probability of a common cause, whether the preponderancy, or whether the tendency to have how much synergy you think is in the signal, does that change across time or across learning? Or is that plastic?
So that is something that people in ML don't really study because we typically fix the modalities first, and then we start looking at multimodal fusion methods and quantification afterwards. But something we're recently looking at is how can we better understand modality importance. So can we pre-select within the modalities the ones that have the highest opportunity for synergy, and we use them based on these information theoretic measures, and based on that you can then choose those modalities to be a priority for fusion. So personally, that is probably going to be very important, especially as we scale to settings with more modalities where you have a choice to choose within which subsets to use. And you may not want to use all of them because of computational resources and constraints.
Thanks.
Okay, let's move to the next talk by Daniel Mitropolsky from Columbia, who's going to talk about formal language theory.
Hi, everyone. So I know we're running a bit behind schedule, so I'll try to keep this short. Maybe make up a little bit of lost time. My name is Dan. I'm like in the transition period where I just finished my PhD. Christos yesterday told you basically about almost all of our joint work and the bulk of my thesis, which is basically about studying algorithms in this biologically inspired computational model, the NEMO model. You know, it's some abstraction of biological principles from the brain, and then we, in order to eventually seeing if this kind of model is a good candidate for describing the brain or not, we approach it as theoretical computer scientists and ask, you know, what kinds of problems can be solved in it. So in this lightning talk, I'm going to zoom in on a very particular implication from this theory that Christos didn't mention, and I think it's interesting. And basically what I'm going to try to convince you of, oops, okay, this is a little, I'll just scroll, is that studying these kinds of frameworks, a computational model like NEMO, might be useful in other unexpected ways. It might yield consequences in some other area of study that you're perhaps more interested in. And the kind of rough analogy I have in mind, which might be a bit too crude for the theoretical computer scientists in the room, is, you know, in the early days of complexity theory and cryptography, these communities were like somewhat disjoint, or perhaps I would say people in complexity theory, many weren't that interested in the results coming from cryptography. They didn't think that those definitions were very important. But sort of a big changing point was when a very famous theorem called the PCP theorem, which is a new characterization and a very important characterization of NP, was proven using techniques and ideas that kind of came about through the crypto literature. And so then suddenly a lot of complexity people started to pay attention to those ideas. And now, of course, you know, these are really intertwined fields in really deep ways. In fact, good. So Christos and Max talked about it yesterday, and I'm going to give you a super quick, ultra fast definition. And since this is a lightning talk, it'll just give you a flavor. You know, there will be like details I won't have time to pin down. So I'm going to show you why studying this weird computational model is useful even outside of even if you're not that interested in this computational model. So let's very quickly go over what NEMO looks like. In NEMO, you have brain areas, which are areas with some fixed number and neurons each. And each area is initially connected as a directed random graph, where each edge is sampled with a fixed probability p. This is a directed Erdős-Renyi random graph. Okay. You also have pairs of areas which may or may not be connected in your particular instance of this model. Okay. And if they are connected, then we sample edges from one area to another with the same fixed probability p. We model local inhibition through the following abstraction. We assume that at any time in every single brain area, only k neurons in an area can fire, where k is some constant that is much smaller than n. So this is how we sort of implicitly model the cumulative effect of various inhibitory mechanisms localized to areas. And what does firing mean? Well, you know, I'll just gloss over this slide very quickly. Firing is the operation that kind of defines this as a dynamical system. So you have some starting conditions, but as the system evolves, at each time step, you compute the input for every neuron, which is just the sum of its incoming synapses. This is a la artificial neural networks. Then we enforce that local inhibition principle. We select the top k neurons in each area by their total input. And these are the ones that fire in the next time step. Okay? And the last ingredient that makes NeMo at least grounded in biology, from my perspective, is that synapses only evolve based off some local weight change principle. And NeMo studies the simplest possible rule you could sort of define, which is a Hebbian plasticity rule. So for two neurons that fired immediately one after the other, we scale the weight of that edge between them by some multiplicative factor. So that's like a flavor of this computational model. Now, why did we initially become interested in this model? Because there were results from experimental neuroscience suggesting that these kinds of principles, a top K winner takes all principle and so on, is useful in the olfactory system of various animals like the fruit fly and the mouse olfactory cortex. But I guess we really became interested in this when we started to sort of play with this dynamical system or computational model and finding that it has very interesting properties. In particular, if you sort of do the simplest possible experiment, you get something interesting. So the simplest possible experiment is you set some neurons in one area to fire, and you observe what happens in another area where at time step 0, nothing was firing. Okay? And you let the dynamical system evolve over time, and the conclusion, and if you've been to any NeMo talk, you've heard this, is that the system will converge to a single set of firing neurons in this second area B. So like very quickly sketching why or what this even means. At the first time step, you get some random subset of K neurons in B. Right? By symmetry, it could be any set of K neurons. It's the ones that have the largest number of edges from those firing neurons in A. But the problem is, as time goes on, new neurons in B will be selected in the top K operation. Why? Because you have neurons firing in B from the previous time step, and you have recurrent inputs. B is itself a GNP random graph. So like the next winning set, it has like some overlap, but very small. And so these kinds of things dance around and move. But as a property of both the random graph structure and plasticity, the Hebbian plasticity rule, this eventually, and relatively quickly, I should say, depending on the parameters you initialize the model with, converges to a single set of neurons in B. And in fact, we can prove that this set of neurons has additional properties that make it interesting. For example, this is intuitive if you sort of followed what I was just saying. The probability of an edge inside of that set, which we converge to in B, the incidence of edges is higher than the sort of default probability of an edge, which was that constant P of the Erdős-Renyi random graph. And for example, if you fire this set of neurons, it will sort of self-perpetuate. It will always summon itself in the dynamical system. So this is really what inspired our deeper study of this model. We saw this operation. It fell out of the simplest possible experiment you could set up with these seemingly extremely simplistic biologically inspired ingredients. And so then we sort of asked, well, how much more can this do? What else can you do with these representations? And so incidentally, if you know about Les Valiant's work on neural items, it's sort of related, but key differences make these sets have all these additional properties. So you can do more things with these. And so like there's many operations we study that you can improve, that you can do. But as like a quick example, you can do things like this. You can have two assemblies in two areas and let the dynamical system fire to create a third assembly in a new area, which will be strongly connected to both of these assemblies. And then you can start to maybe do some sort of combinatorial logic among these representations. So basically this led to the kind of work that us NeMo folks do to ask what other kinds of algorithms can you implement in the system in the regime where these ensembles, which naturally arise from the dynamical system, they aren't some sort of axiomatically baked in ingredient, assuming that these assemblies are the input representation of some sort of symbols or something like this, what kind of computation can you do? So one of our, I think, most exciting results is that we can implement a parser in this dynamical system with assemblies representing words as inputs. Okay, so without getting into too much detail, what do I mean by parsing? So what we implemented, at least initially, I should say, is a dependency parser. Basically, you have to feed in a sentence word by word. So I'll show you in a second roughly what that means in the dynamical system. And by the end, it should store or output, compute the syntactic parse tree or some tree representing the grammatical relationships of that sentence. And what we show is that you can parse in Nemo in like relatively efficiently, roughly in time, linear in the length of the sentence times D, where D is the number of dependent or embedded clauses in the sentence. So indeed, as you have like more and more nested structure in a sentence, this becomes harder. So I should say quickly, dependent or an embedded clause is something like, I saw the man who works at the store, or something like that. And indeed, in even trying to come up or formalize an algorithm for this problem, the main difficulty was how to handle dependency. So let me like sketch why that's non-trivial, or how you even do parsing in Nemo. So here's like kind of the first version of Nemo. And this one is not going to handle dependency. But what you might do is, and again, and so I should say, when in this relatively new area of study, we're both sort of defining and choosing how to represent input and output, and then also studying whether there are algorithms to solve the problem in that regime. So this assumes a specific representation of input to the system. Okay, good. So roughly you have a bunch of those Nemo brain areas for various syntactic constituents or tags of the dependency parse, if you know what that is. So we have like an area for verb, object, determinant, subject, and so on, which will in which assemblies will activate corresponding to those syntactic constituents of the sentence as we parse. And there'll be a special area called lexicon, which will have a pre-learned assembly for every word in the lexicon. So this also clarifies that what we showed the Nemo algorithm we're constructing doesn't solve a learning problem. We're asking whether in the Nemo dynamical system you can implement a parser if I can bake in assemblies for each word, which I assume have been learned somehow. And those assemblies encode, they connect to the graph in certain ways. So the question is, if I then activate those assemblies one after the other in order of the sentence and let the whole dynamical system run, will it, in certain range of parameters, will it converge with high probability and stably sort of create a representation of the dependency parse tree? So the answer, so I'm not showing you the actual algorithm or the details here, but in short, the answer is yes. But with what I showed you here, with these kinds of ingredients, you will only be able to recognize the regular languages. The consequence of which you won't be able to handle any of embedded or dependent constituency, which is sort of the most interesting thing in language. So the question is, how might you extend this? How would we modify this model and the algorithm to handle that? Well, here's like an initial idea. So here's an example of a sentence with a dependent clause. The man who lives next door works at the University of California, Berkeley. Okay, so maybe what we'll try to implement in Nemo is that when we encounter the start of an embedded clause, so let's say the first comma there, we'll reinitialize the state of that Nemo-based device to its initial state before, like, when it hears a new sentence. And then we'll parse the embedded clause. Okay? And then upon the end of the embedded clause, so the second comma, let's say, what we'll do is we'll pass through the saved sentence before the embedded clause to try to restore the state of the outer clause containing this one. Okay? And then we'll continue, we'll skip over the embedded clause and continue from the words starting after the second comma. So this could do something. You can define a set of languages recognized by a device like this. And it's implementable in the Nemo architecture, but it doesn't link the clauses in any way. So if I then try to read out, for example, the syntactic tree from after I parse the sentence, I would only have the outer sentence, and I would lose all the embedded clauses. So what do? Well, we sort of do what Nemo is good at. Nemo is really good at taking even like a complex, let's say, set multitude of assemblies that are already encoding something and projecting them or merging them into a new area, as long as it hasn't sort of reached capacity in some sense. But it's pretty good at like projecting or firing some existing representations into a new area to create a merged representation that can then relatively reliably get back those. So we're going to sort of use that. We're inspired by this. We thought maybe the following algorithm would work. So when we see the start of that clause S, we'll project the referent of the outer clause to a new area. So before I had these, just draw this here, subject, verb. So basically to handle this, we need a new Nemo area. Again, I'm just giving you a flavor of how this works, which we'll call dep for dependency. So when we start an embedded clause, so the man, comma, we know this is going to happen. I can tell you about the plausibility, why we assume that there's always commas. It's a simplifying assumption. So Good. So when we encounter that, we project the referent to the other. The referent is the word man. It governs the dependent clause. So let's say we have a representation for man, an assembly that's been activated in subject. We'll start firing it into dependency. And then when we parse the dependent clause and we get to the verb, the main verb of the embedded clause, the man who lives next door, because verbs govern, they're sort of the root in parse trees of sentences, we'll project this into dependency as well. So we'll link them by activating an assembly in dependency so that you could then go from this referent through this area to restore the embedded clause. Okay, so why is this interesting? So I should say, what I'm going to fully go leave out here are our experimental and theoretical results showing that this algorithm works, and you can parse some subset of English sentences of relative complexity. And that is really a result about the NeMo model and really about random connectivity and graph simplicity, showing that those ingredients somehow are sufficiently strong to such that a dynamical system with many firing assemblies converges with high probability in reasonable parameter settings. So that's a result. That's a sort of a graph theoretic result. But let's look at this in a very different way. Let's abstract as much as possible this algorithm and sort of forget about the NeMo implementation of the algorithm. So you can abstract this algorithm really as a finite state machine with a fallback and reparse ability, right? When it encounters the end of an embedded clause, it falls back to the beginning and reparses up to the beginning of that embedded clause. Okay? And what we show is that this algorithm that we came up with really showing implementability in the NeMo model in mind, that was the chief goal, in fact recognizes the context-free languages. So the context-free languages, very roughly, are these kind of languages defined by sets of rules where you have non-terminals mapping to strings of terminals and non-terminals. Okay? So, without just this is one slide on formal language theory, in a non-deterministic finite state automaton, which only recognizes the regular languages, you have some transition function, right, that goes from symbols to in states to other states. But the abstraction of the algorithm I just showed you is something we term a fallback automaton. And in this version, in this definition, the transition function also marks symbols as seen as it goes, or it marks them with the current state of the machine, Q. And it can also have, the transition function can output an additional symbol called the fallback symbol. And when it does so, the machine goes back to the most recently marked, to the word that has been marked with some state as opposed to just the red symbol S. So this gives you a flavor. It's basically a finite state automaton that can fall back in the sentence. And the proof is non-trivial, but this recognizes the context-free languages. I'm almost done. Okay. Now, why is this interesting? Well, the context-free languages have their origin in linguistics, but they have a complicated history in linguistics. They were originally defined and studied in order to characterize the grammars of natural languages. And this was extraordinarily influential. In fact, it's very influential up to today. I think most linguists would argue that the majority of natural language syntax is captured by context-free grammars. However, later on it was found that languages do have context-sensitive features. The most famous examples are from Dutch and Swiss German. I love telling people about those, so please ask if you're interested. And there are my very arguable examples even in English. And it's also a sort of a bad formalism in the other direction, because natural languages tend not to make full use of a CFG's power. They tend to have very limited, it's almost like a subset, but also a superset of CFGs at the same time. But nevertheless, we found a new characterization of this relatively good formalism for languages through studying, simply through trying to find an algorithm for parsing that works in this neurally inspired architecture. And I should say, among open questions, our results kind of left many things open, because what I just showed you, the new characterization of context-free languages, depended on how we abstracted that NeMo parsing algorithm. If I abstract it in a slightly different way, it's not clear that I actually get all the whole set of context-free languages. And so an open question left by this work is, and I don't really know the answer to this yet, there seems to be, if you abstract this algorithm slightly differently, some class of formal languages between the regular languages and context-free languages, which maybe is actually a better model for natural languages, even though that will also miss the context-sensitive features of languages. So that's another open problem here. Great, so that just gives you a flavor of how, studying one area or domain might yield consequences or results in something very different. Thank you.
Okay, quick question, please. Okay.
Hi. Okay. Hi, Daniel. Quick question. So in this NEMO model, you have a sort of a global sort of definition of what it means to inhibit. So as in top K, can this be implemented locally? And if it were implemented locally, would it change the functionality?
I don't know if maybe some approximation can be implemented locally. I don't know if Mirabel or Max know about this. Like an approximation can be implemented with.
Yeah, you can set up like a bipartite graph, like excitatory on one side, inhibitory on the other side, and like in a couple rounds, it stabilizes to top K.
Oh, good. So, well, yes, if you like explicitly model inhibitory neurons, then it can be implemented locally.
Yeah. I mean, you have to, if you include inhibitory neurons, connect them in the right way, then that can be done locally just using like inhibitory neurons.
Yes, I suppose that's like the justification for why we assume this is just an ingredient in the model, and we don't model inhibitory neurons explicitly. But in fact, it can be implemented this way. Yes, that's very important.
Great. Thank you, Dan. Let's continue with the next talk.